we're going to talk about phase portraits for linear systems having real eigenvalues. Before we do so, let's review some ideas from before about straight line solutions. We have the following theorem. Assume that we have a two-dimensional system d capital Y dt equals a times capital Y, where A is a 2 by 2 matrix having constant coefficients. We'll assume that we have a solution capital Y which lies along a straight line ax plus by equals c. First, the solution that we're seeking is in the form capital Y equals u of t times capital V plus capital Y sub 0, where capital V is a vector that lies perpendicular to the line, and y sub 0 is a vector that lies on the line. Next, there exists a constant lambda such that du dt equals lambda times u. That is, u of t is a constant times to the lambda t. Third, the vector capital Y sub 0 is an equilibrium point for the two-dimensional system. That is, a times capital Y sub 0 equals the 0 vector. And finally, the constant lambda is an eigenvalue of the matrix A, while V is an eigenvector corresponding to lambda. That is, A times V is lambda times V. Using this theorem, we can make a few more general definitions. Let's say that A is more generally an n by n matrix. The origin, capital Y of 0 equals 0, is the only equilibrium point if and only if A is a non-degenerate matrix. Second, we say that a scalar lambda is an eigenvalue for A if there exists a non-zero vector V such that A times V is lambda times V. That is, lambda is a root of the characteristic polynomial determinant of A minus lambda in. And finally, if lambda is an eigenvalue, we say that this vector V is an eigenvector associated to lambda. Using this, we can write down an algorithm to determine straight line solutions for a 2 by 2 matrix. Step number 1. Compute equilibrium points capital Y sub 0 as solutions to the system A times capital Y sub 0 equals the 0 vector. Number 2. Compute eigenvalues lambda as roots of the characteristic polynomial. We just have to make sure that lambda is a real number in order for all of this to work. Third, compute eigenvectors capital V via the system A times capital V is lambda times capital V. And finally, we can return the solution that we seek to the system d capital Y dt equals A times capital Y, satisfying the linear equation A times x plus by equals c as the function of the form capital Y of t equals e to the lambda t times the eigenvector capital V plus the equilibrium point y sub 0. We're going to use this today to plot phase portraits for linear systems having real eigenvalues. Today, let's consider a two-dimensional linear system with constant coefficients. That is, dx dt equals a times x plus b times y, and dy dt equals c times x plus d times y. We can express all of this as a product of matrices. That is, d capital Y dt equals a times y, where capital Y is the vector ax, y, and capital A is the matrix A, B, C, D. Recall that we found earlier in the course that both x and y are solutions to a second-order differential equation of the form d squared y dt squared plus p times dy dt plus q times y equals 0, where p is the constant negative a plus d, and the q is the constant ad minus bc. Today we're motivated by the following question. Given just p and q, how do we plot the slope fields of these equations? We're going to recall a few facts and definitions before we get to answering this question. First, recall that solutions capital Y sub 0 to the system A times capital Y sub 0 equals the 0 vector are called equilibrium points. Since Q is the determinant of A, namely AD minus BC, we see that Y sub 0 is the origin if and only if Q does not equal to 0. Eigenvalues lambda of A are roots of the characteristic polynomial, which can be expressed as lambda squared plus p times lambda plus q. Setting this equal to 0, we can use the quadratic formula to find that lambda equals minus p plus or minus the square root of p squared minus 4q, all divided by 2. Observe that lambda is a real number if and only if the discriminant p squared minus 4q is greater than or equal to 0. Next, eigenvectors, capital V, associated to an eigenvalue lambda, satisfy the system A times capital V equals lambda times capital V. In many cases, we can simply choose capital B to either be the vector b, comma, lambda minus A, or the vector lambda minus d, comma, c. Finally, putting all of this together, recall that straight line solutions, capital Y of t, are in the form e to the lambda t times the eigenvector v plus the equilibrium point y sub 0. We're going to put all of this together to state and prove the following proposition. Let's consider a two-dimensional system, d capital Y dt equals a times capital Y, and let's assume that q does not equal to 0, and p squared minus 4q is positive. Recall that p is the constant negative a plus d, and q is the constant ad minus bc. The first of our results states that the only equilibrium point is capital Y sub 0 equals the origin. Second, there are two distinct eigenvalues, lambda 1 and lambda 2, and they are both real numbers. Third, any eigenvectors v1 and v2 associated to these eigenvalues form a basis for R2. And finally, the general solution to this two-dimensional system is capital Y of t equals k1 times capital Y1 of t plus k2 times capital Y2 of t in terms of the straight line solutions, capital Y sub 1 of t equals e to the lambda 1 times t plus the eigenvector v1 plus the equilibrium point y sub 0, and capital Y sub 2 of t equals e to the lambda 2 times t times the eigenvector v sub 2 plus the equilibrium point y sub 0. We'd like to give a sketch of why this proposition is true. First, notice that because q is the determinant of A, and we are assuming that q does not equal to 0, this means that our matrix A is a non-degenerate matrix. Hence, the only equilibrium point, capital Y sub 0, must be the origin. Second, in order to make a statement about the eigenvalues, let's note that our characteristic polynomial can be expressed in the form lambda squared plus p lambda plus q. Since we're assuming that our discriminant, p squared minus 4q, is positive, this means that we find two roots, lambda 1 and lambda 2, in terms of the quadratic formula as you see here, are real and different from each other. Now let's say that capital V sub 1 and capital V sub 2 are eigenvectors associated to these two eigenvalues. Well, there's a theorem from linear algebra that states that as long as we have eigenvectors associated to distinct eigenvalues, then they form a linearly independent set. Since we're dealing with R2, and R2 is two-dimensional, then the set consisting of V sub 1 and V sub 2 must form a basis for R2. Finally, let's consider an initial value problem, d capital Y dt equals a times capital Y, where perhaps initially capital Y evaluated at t0 equals some vector, let's call it z. By the existence and uniqueness theorem, we know that there exists a unique solution. We're going to try to find it. Well, we can find scalars c sub 1 and c sub 2 so that this vector capital Z is a linear combination c1 v1 plus c2 v2. This is because we know that v1 and v2 form a basis for R2. Now let's denote real numbers k1 as c1 times e to the negative lambda 1 t0, and k sub 2 equals c2 times e to the negative lambda 2 t0. We put all of this together to see that our linear combination, capital Y of t equals k sub 1 times capital Y sub 1 of t plus k sub 2 times capital Y sub 2 of t is the unique solution to this initial value problem. But really, this is what it means to say that we now have the general solution because this works for any initial value, capital Y sub evaluated at t0 equals c. Now, let's put all of this together into an algorithm. What we like to do is assume the following, that q is non-zero and p squared minus 4q is positive. We're going to perform the following steps in order to sketch the slope fields For a two-dimensional system, dy dt equals a times y. Step number one, let's compute the eigenvalues, lambda 1 and lambda 2, as well as the eigenvectors, v sub 1 and v sub 2. Observe that our assumptions will make it so that these will all involve real numbers. Step number two, this is really the crucial part. Let's draw a line in the direction of our eigenvector v sub 1 going through the equilibrium point, capital Y sub 0 equals the origin. If the eigenvalue lambda sub 1 is positive, we'll place arrows on this line going away from the origin y sub 0. If the eigenvalue lambda sub 1 is negative, we'll place arrows on this line moving in towards the equilibrium point y sub 0. We can do the same thing for the other eigenvector v sub 2 and the other eigenvalue lambda sub 2. Note that this will divide the plane R2 into 4 regions. Finally, in each of these 4 regions, we can sketch curves with arrows on them, which follow the direction of the arrows on the lines from the previous step. It'll be a little bit easier for us to explain this via an example for this to make a little bit more sense. Now, once we've done this algorithm, we'd like to write a few definitions. First, the plot of these curves is called a phase portrait, and the plot of the arrows, of course, is called the direction field or the slope field. Second, let's say that both eigenvalues are negative. Then the equilibrium point, capital Y sub 0, is called a sink. In particular, if lambda 1 is less than lambda 2 is less than 0, then all solutions, capital Y of t, tend to the origin as t increases without bound, where most move towards the line corresponding to the eigenvector v sub 2. Sinks, in this case, are called stable equilibria. Now let's say that both eigenvalues, lambda 1 and lambda 2, are positive. Then the origin is called a source. In particular, if lambda 1 is greater than lambda 2 is greater than 0, then all solutions move away indefinitely as t increases without bound. Most of the solutions emanate from the line corresponding to the eigenvector v sub 2. Sources are called unstable equilibria. And finally, let's say that maybe one eigenvalue is positive while the other one is negative. Then the origin is called a saddle point. For example, if lambda 1 is less than 0, but lambda 2 is greater than 0, then some solutions will tend towards the origin along the line corresponding to v sub 1, whereas other solutions tend to move away without bound, as t increases without bound, along the line corresponding to v sub 2. Notice that saddles are neither stable nor unstable because they depend upon the direction in which approach the equilibrium point. Let's end today by going over 3 different examples. First, let's consider this two-dimensional system where our matrix A is -1, 0, 0, and -4. We can compute that the eigenvalues and eigenvectors are lambda 1 is -4, corresponding to the eigenvector v sub 1 is 0, 1, and lambda 2 equals -1, corresponding to the eigenvector 1, 0. Now let's try to plot the phase diagram and the slope field. You can see on the left, we tried to place in the curves as well as the arrows corresponding to them. Let's see if we can make a little bit more sense of this. First, the origin is our equilibrium point y sub 0. Notice that here we have 2 lines. The first one, which is just the x-axis, this corresponds to v sub 2. The second one, which is the y-axis, this corresponds to v sub 1. Notice that we have arrows on these 2 lines moving in towards the origin because our eigenvalues, lambda 1 and lambda 2, are negative. That is that the origin in this case is considered to be a sink. You can also see that all of the lines are not just moving in towards the origin, but we can also see in some sense how they're curving a little bit. Notice that in this case, lambda 2 is greater than lambda 1, so our curves seem to be moving in towards the line corresponding to v sub 2. That is the x-axis. Again, you can see this a little bit more clearly on the right. All of the arrows seem to be curving in towards the x-axis. That is the line corresponding to v sub 2. Again, the origin here is a sink, and recall that a sink is a stable equilibrium point. You can also see this from the arrows. It appears that all of the arrows, no matter where you start, all seem to be moving in towards the origin. Next, let's consider this two-dimensional system where our matrix A is 2, 2, 1, and 3. We can compute that the eigenvalues and eigenvectors are as follows. Lambda 1 is 4, v sub 1 is 1, 1, lambda 2 is 1, and v sub 2 is negative 2, 1. Now here, we'll plot two lines corresponding to our two directions, v1 and v2. You can see here that v1 seems to be moving from the lower left to the upper right, whereas v sub 2 seems to be moving from the upper left to the lower right. In this case, both of our eigenvalues are positive, so we see that at the origin, we'll have arrows moving away on both of these lines. You can see this a little bit more clearly with the arrows on the right-hand side of your screen. Now, if we'd like to get a better idea of how to actually make our curves for a phase diagram, remember that the idea is that we should have curves that start along the line V2 and move outwards. You can see this as the blue lines on the left seem to be moving along the line corresponding to V2, and then they slowly curve upwards. This is the idea. They emanate on what looks like it's from the line V2, and then they curve and foil out. Notice that the origin is a source. In this case, it is an unstable equilibrium point. It is a source because you can see from the arrows on the right-hand side of your screen that all the arrows seem to be emanating away from the origin. In our last example, let's consider the two-dimensional system corresponding to the matrix 8, negative 11, 6, and negative 9. We can compute that we have the eigenvalues. Lambda 1 is negative 3, v sub 1 is 1, 1, lambda 2 is equal to 2, and v sub 2 is 11, 6. Again, we have two lines, but we have to be a little bit careful here. We have the first line corresponding to 1, 1, and we see that in this case, the arrows must be pointing in towards the origin. We have the second line corresponding to the vector 11, 6, but in this case, the arrows are pointing away from the origin. Now, once we have these, we see that the situation is very different from what we had before. It's not as simple as the arrows either moving in towards the origin or moving away from the origin. This is the concept of being a saddle point. We have to be very careful to look at the various regions to see how the arrows now move along. You can see that the arrows seem to be starting on one side, they kind of move up towards the origin, and then they kind of move away and continue moving along. This is why we have to be careful to draw various curves and not just pay attention to the lines. This is why the graphs get a little bit more complicated, but hopefully you can see how this works. Thanks very much for watching.